Hi! This is the final report for the time series prediction team. Oregon State, Capstone Course, Spring 2025. Adrian, Brian, Joe, and Seth. Artificial intelligence and machine learning are driving innovation. Our team, as introduced on our title slide, proposed a project for our capstone time series prediction that would help us learn by doing. We built a recurrent neural network that forecasts the next data point, such as Corvallis's next day temperature within 4 to 5 degrees, and developed a user interface for selecting datasets, training the model, and generating predictions. We believe these capabilities will inform better decisions, manage risk, and drive intelligent control across business, science, and government.
In terms of highlights, the graphical user interface that we created for our project makes our work accessible and usable, but we also think our project adds great value to users as an educational tool that others can use to learn more about RNNs and the underlying math. Our primary RNN is object-oriented and does not rely on a machine learning framework like PyTorch that hides the underlying mechanics. The RNN in our project was built to be flexible by incorporating configuration files that allow a user to quickly modify the network parameters and run multiple configurations in parallel for experimentation. On the left side of the U, you can see the upper part of a human-readable JSON configuration file that defines RNN parameters like the data fields to be used for prediction and target, the dimensions of the input, hidden, and output layers, the number of epochs, sequence length, and learning rate. The configuration files also enable checkpointing of all internal weights and biases so training can be saved and continued. On the right side of the slide, you can see multiple instances of our RNN with different configurations running in different threads thanks to the multiprocessing utility we developed. This enables multiple user-defined experiments to run in parallel.
Our team defined the high-level requirement of building a time series predictor using neural networks and divided the work into tasks like data preprocessing, model prototyping, UI design, integration, and testing. We coordinated through weekly 2-hour meetings and ongoing chat, regularly reviewing our scope with each other, and we also met with instructional staff. We adjusted as needed. Everyone contributed effectively. Although our plan focused on learning neural network theory and building a predictor from scratch, we not only met those core objectives, but also implemented stretch goals, like building a GUI wrapper around our code and enhancing network performance. We also went beyond our stretch goals by running a PyTorch RNN on hardware with GPUs for comparison. We faced a steep learning curve from neural network theory to debugging multi-dimensional tensors, balancing research, coding, and team dynamics. We overcame these hurdles through teamwork, incremental development, unit testing, logging, debugging, and effective communication. As a result, we gained in-depth experience with neural network architectures, data processing using NumPy and Pandas, PyTorch, Qt, Jupyter, parallel execution, GPUs, and collaborative GitHub development.
Hi. I implemented neural networks using Python libraries like NumPy, Pandas, and PyTorch, experimented a little with different architectures, and ultimately leveraged PyTorch for compact and simpler code. Translating the underlying linear algebra and backpropagation mathematics into working code was challenging, and debugging often involved tracing mismatched matrix dimensions. To iterate quickly in an effort to meet our project goals, I built an end-to-end prototype UI in Jupyter notebooks with interactive widgets and also explored basic Qt development for the same end. Finally, collaborating with a larger team deepened my proficiency with Git and GitHub. Next, I want to show some screenshots of my development efforts. First, I want to show the Jupyter notebook that I used to prototype a graphical user interface that used Jupyter widgets. This single notebook integrated all of the elements of our project, from reading data to training and predictive output. I had barely used Jupyter notebooks previously, and I found them very easy to use and intuitive in terms of incremental development and documenting my ideas. Next, I worked on a Qt user interface based on Joe's first iteration of GUI code. My Qt user interface did basically the same thing as the Jupyter notebook I showed on the last slide. But since the team planned to use Qt, I wanted to try to translate my notebook into this new framework as a prototype for what we might be able to create. My next slide shows prediction output from a PyTorch RNN that I derived from Adrian's RNN that used only NumPy. The graph shows predicted maximum temperatures versus actual temperatures after training was complete. I iterated over the RNN parameters a bit to get predictions that were roughly within 5 to 6 degrees Fahrenheit of the actual temperatures. And my last slide shows the training loss for my PyTorch RNN versus Adrian's same RNN. At first, I thought maybe the PyTorch trained slower because I wasn't taking advantage of GPUs. But Seth ran the same PyTorch RNN on a system with GPUs, and I think Adrian's RNN still performed better overall. I have to give Adrian credit for all the work he did to enhance the network he built. It was relatively fast at training and better at prediction.
Hi, I'm Seth Makoviak, and through the following slides, I'm going to do my best to cover my own project responsibilities while touching on the project planning, challenges, deviations, and learning along the way. With our initial project objective being focused on learning the inner workings of a neural network, leading to the ability to develop one from scratch, I took on finding credible resources to learn from, both textbooks and Vic Pachuri's open source learning tools that our final neural network was based off. Upon doing this, our team was able to have a very coarse RNN up and running by week 3, as was shown in Progress Report 1. Those predictions were very coarse and constrained. They were a significant step in proving out our approach. Upon receiving input and feedback from our TA and guide, our focus was shifted and my responsibilities were pivoted towards importing, cleaning, and formatting data to be used by the RNN training process. Most of this was encapsulated in the data preprocessing class and split function that allowed a simple CSV to be efficiently relayed to the neural network training process and simplify the implementation by reducing the number of lines of code that aren't directly relevant to how the neural network is trained. This redirection was not anticipated at the time, but forced our team to flex the strength of collaboration and take on the real-world challenge of continuously evolving goals. In turn, the redistribution of responsibilities allowed our team to surpass our initial objective. As part of surpassing our initial objective, we were directed to test the benefits and/or drawbacks that different hardware resources have to offer. In direct collaboration with Brian, PyTorch was used to compare training performance using a GPU rather than a CPU for the matrix multiplication. The graph shown provides this one-to-one comparison with all training arguments identical throughout the process. The results, along with the elapsed time at each epoch, were stored and reviewed, showing that the CPU actually overperformed the GPU. With further research on this topic, it was determined that our RNN was fairly simple, with merely 3 input variables and a single target variable, and unable to take full advantage of the GPU's capabilities. As a continuation of our CPU versus GPU stretch goal, we chose to iterate over multiple variables that affect how the RNN is trained. Given that our visual perception is limited, the argument performance graph shown provides a 3D surface plot representing the effects both the batch size and hidden dimensions have on the training time per epoch. It can be seen that the hidden dimensions is negligible while the batch size has a large initial impact before plateauing. Again, the CPU still pulled out ahead, but the difference was reduced significantly.
This project involved many different problems and solutions. The whole team wanted to learn more about neural networks, and we were excited to learn. A significant portion of my time was spent researching the underlying math of neural networks and solutions to improve neural network performance. I feel like I only scratched the surface of what is possible. This is a graph of one complex sine wave that our RNN was trained on. The graph shows the progressive improvement of the predictions that the RNN made up to 240 training epochs. After 240 epochs, the loss was continuing to improve, but the progress was diminished. I produced the sine wave myself to repeat 10 times over the 100,000 line CSV file. I produced additional columns of data through feature engineering to improve performance. I initialized the weights randomly 100 times for 5 distinct datasets. The goal was to see the distributions at the end of training to see the implications of randomly produced weights. There was a relatively consistent distribution of training loss and validation loss. I took advantage of our ability to generate many different configuration files and run the training in parallel to save time. The file names on the figure represent the configuration file parameters. The file names reference the number of hidden dimension, the learning rate, and the range of possible slice lengths. It would be possible to continue the training for the examples that have not appeared to plateau. This picture shows the comparison of 2 log files containing all network parameters at each step of training that could be used for troubleshooting. When I refactored the code, I wanted a method of comparing the original working RNN code that we used as a starting point against the new refactored code. Any discrepancies would be highlighted to narrow down where the problem existed. This was extremely helpful to solve bugs during the refactoring process.
I'm Joe, and this is my development throughout this project. So initially, I worked on developing object-oriented RNN based off the DataQuest recurrent neural network. This all started as part of our individual learning and understanding. This consisted of researching and understanding recurrent neural networks, watching the data test tutorial, taking that code from that tutorial, understanding it, and then putting it into a class and creating an object-oriented version, and then actually testing it. This was just mostly the sandbox code. It did not make it into our final version of the project. Next, and probably my main contribution to this project, was creating the graphical user interface. This was done using PySide6. There were quite a few steps to actually doing this. One was researching, understanding how to work with PySide6. Previously, I'd only built web apps, so this was my first desktop implementation. After that, a visual mockup was made in PySide6, so just really creating the pages, but no actual connection to our model or any real computations done yet. After this, we gathered feedback on changes to make and directions to go, and then learning how to understand to integrate this actually with our model, then actually integrating the RNN model with the UI, and then from there it was a bit of a cyclical cycle with each pull request of gathering feedback and making changes. And one thing to note, regular pull requests at each milestone is really important to this process and really helped with the feedback and making sure we were all on the same page. There were some planned deviations. Initially, we were all going to just work on parts of this recurrent neural network, but eventually it was decided that the GUI was no longer a stretch goal and that should become a main project goal, so it's what I took on. There were some challenges throughout this whole process. Initially, just understanding how RNNs worked was really difficult. I found the video-based tutorials to be the most helpful because they gave visual representations of how things worked, which is kind of how I learn. On top of that, working on the GUI, deciding which data type to use and which data set, we decided on temperature data since it's relatively easy to work with and it gives us a few options. And then finally, actually integrating our GUI and a model that was in development. There were times when I was trying to integrate things that hadn't been created yet, or the data type was not really set, or things were still in motion. Really just good communication and determining how information would be passed between the model and GUI with that communication was the solution. And then along with that, gathering feedback from pull requests was great for seeing if I was integrating things right and fleshing out different ideas. Just an overview of the different pages of the GUI. There's the start page, which can load the data set, of which we have 2 currently to be used, and then we can train a model based on that data set. Or you can take a previously saved trained model, and you can also load that as well. So if you decide to train a new model, it'll take you to the loading page, which you will wait while the model trains with epic updates. You have 2 options here: wait for it to finish, or you can cancel it, which will bring you back to the start page, or you can stop it, which will save the current waits from however much training you've done and epics you've done, and bring you to the display page where you can enter in a maximum temperature, minimum temperature, and precipitation, and get tomorrow's predicted temperature. And you can save the model configuration here so you can come back to it again.
In conclusion, the project gave us a solid foundation in neural networks, and we explored additional scope beyond our original plan. We ran RNNs in parallel for parameter tuning, we applied transfer learning with pre-trained weights, and we leveraged GPU hardware. This hands-on experience prepares us for a future driven by artificial intelligence, and we're eager to keep learning. Our modular, object-oriented code can easily incorporate GRUs, LSTMs, transformer models, deeper RNNs, and attention mechanisms. Starting June 4th, we hope we can use OSU's HPC DGX system to scale our experiments to larger problems. That's the end of our video. We hope you enjoyed it. Please contact us if you have any questions.